So this is number 3 from the Mechanics 2005. We've got a system, ball of mass 2, uniform rod of mass 1, length of d, rod's attached to a frictionless table by a pivot point P, rotates with an angular speed omega as shown above left. Rotational inertia of the rod is 1/3 m1d2, which we did earlier. Rod strikes the ball, which is initially at rest as a result of the collision. Rod stops, ball moves in the direction right to the right. Express all answers in terms of m1, m2, omega, d, and fundamental constants. So first up, derive an expression for the angular momentum of the rod before the collision. So angular momentum, you guys might have to look this one up, but it is equal to I times omega. All right, I times omega, where I is the rotational inertia, which they give us right here. So we can just go ahead and plug that in for the rod, right? So the angular momentum of the rod is going to be 1/3 m1 d squared times omega. That is an answer that is in the terms that it allowed us to answer in. So that's all we really need to do there. Derive an expression for the speed of the ball after the collision. So it's talking about collisions here. What should we do if we're working with a collision? We should do conservation of momentum. In this case, it's conservation of angular momentum. Now, it might seem a little bit weird to consider the angular momentum of a ball that's moving in a straight line. But if we take the ball as like the instant it starts to move and the pivot point P, we can technically say that this ball is rotating about the pivot point P, right? This little, right, its velocity is in the direction to the right. But if we take it to be rotating, right, about point P, it still has angular velocity about point P, right? It's going to continue to go straight, but it does have angular velocity. With respect to point P, it has angular velocity or angular momentum, sorry. So the angular momentum of the rod is going to equal the angular momentum of the ball, right? Conservation of momentum, momentum before has to be equal to momentum after. Angular momentum is the same thing. Angular momentum before has to be equal to angular momentum afterwards about the pivot point. So we have the expression for the rod already. That's 1/3 m1 d squared omega. That's all good. That's all allowed. Equals angular momentum of the ball. Let's just drop in the I omega there, right? So I omega is the angular momentum of the ball. Unfortunately, neither of these is allowed because we need m1, m2, omega, and d. And we're looking for speed, linear speed, not angular speed. So we need to replace a couple of things here. Let's start with the angular moment or moment of inertia of the ball. Moment of inertia, we know for point particles, which is nice that it gives us a point particle, is mr squared, right? Ball is technically a single point. It's going to be equal to mr squared. So we can substitute in m of the ball, distance from the pivot point for the ball. So we'll get that the moment of inertia is m2, mass of the ball, times d squared. D is the length of the rod and the distance to the pivot point from the ball, which are both allowed in our expression. We can plug those in. We also want V. V can be related to omega by omega times r. So velocity is equal to omega times r, which means omega is equal to velocity divided by r. We can plug in what we have here. The omega for the ball is going to be equal to the velocity of the ball divided by the radius from the pivot point again, which is d. So we can substitute in v over d for omega. So we have two things to plug in here. m1 d squared omega. And the nice part is d is allowed, so that's cool. m2 is allowed, d is allowed. So all this stuff is stuff that we need to be solving in. So we'll get m2 d squared times v over d. A couple things will cancel here, right? D will cancel with d squared, which is good. But that's really all to start. I'm going to hop over on the other side to finish this one. So we'll have 1/3 m1 d squared omega equals m2 d v. D will cancel with d squared. M2 we can divide over, and our velocity is going to be equal to 1/3 m1 over m2 times d omega. There is our expression for the velocity of the ball after the collision. I should probably make that 1/3 a little bit bigger so I don't think that it's part of the numerator here. This is a 1/3. 1/3 m1 over m2 times d omega. Okay, so assume the collision is elastic, calculate the numerical value of the ratio m1 to m2. So you might think, right, if we look at this, we have the ratio m1 to m2 right here, right? We could just multiply by 3, divide by d, divide by w, and be good to go. The problem is v is not allowed. So we need something to replace v with, right? We need another equation that we can get rid of this v so that we can have a relationship that is dependent on d omega and not on v. So we need a second equation, and it tells us here that the equation is, or the collision is elastic, and we should know that in elastic collisions, kinetic energy is conserved. So the kinetic energy of the rod is going to be equal to the kinetic energy of the ball. Because the rod is, all this is true because the rod is stopping after the collision. If the rod doesn't stop after the collision, we have a whole different, because we have to add kinetic energy of the rod afterwards. But because the rod stops, it's giving all of its momentum and it's giving all of its kinetic energy to the ball. So the rod is rotating, so it has rotational kinetic energy, which is 1/2 I omega squared. The ball has linear kinetic energy, which is 1/2 mass times velocity squared. So here we have another equation that's going to involve v. We can substitute in, hopefully, or substitute the other way, whatever works, and get something where we can come up with this ratio here. So we should notice right off the bat, there's a 1/2 on each side, so we can cancel that. I is going to become the 1/3 m1 d squared times omega squared equals, this is the mass of the ball, so m2 v squared. So we could do this a couple ways, actually. We could go ahead and solve for v here and then set them equal to each other. I'm going to plug in v from my momentum equation into v in my kinetic energy equation and solve that way. So I'm just going to replace v, right? We still have an equation that has v in it that's not allowed. So here I have an expression for v that doesn't have anything that's not allowed. So I can plug that in and we can go from there. So 1/3 m1 d squared omega squared is equal to m2 times all of this squared. So 1/3 m1 over m2 d omega squared. So we square some stuff out here. 1/3 m1 d squared omega squared equals m2 1/9 m1 squared m2 squared d squared omega squared. So you square everything, right? We square everything out and we get some nice things happening, right? Omega is going to cancel with omega. D squared is going to cancel with d squared. M2 squared will cancel with m2 here. M1 squared will cancel with m1 over there. And we end up with 1/3 equals, everything else cancel on this side, 1/9 m1 over m2. Both of the squares canceled, right? This one canceled with that m2. This m1 canceled, or this square canceled with that m1. And we're left with this little ratio right here, which if we multiply 9 up to the other side, we get 9/3 equals m1 over m2, which is equal to 3. So the ratio of M1 to M2 is 3. It's a ratio, so it doesn't have units. There we go. Last part to this problem. A new ball, same mass M1 as the rod, is now placed at distance X. So it's no longer out here at distance D from the pivot point as shown. Assume collision is elastic. For what value of X will the rod stop moving? So we want to do the same thing that we did last time. We're going to use two equations, the momentum equation and the kinetic energy equation, except this time we're going to try and solve for X. So we'll solve kinetic energy, we'll solve momentum, we'll replace V, and we'll solve for X. So I'm going to start with momentum. Momentum of the rod is going to equal momentum of the ball. Again, because the rod is going to stop. So we'll get I omega is equal to I omega. These are for the ball. These are for the rod. We know I for the rod is 1/3 M1. This is still D. So M1 D squared omega. I is going to be M1 X squared, right? Because the distance now is X, it's not D anymore. At times we should replace omega again with the velocity of the ball divided by X this time, right? So last time we replaced this with V over D, but it's not at distance D anymore, it's at distance X. So X will cancel with X squared, and for the, and the M1s cancel actually too. M1 will cancel with M1. We'll get 1/3 D squared omega is equal to X times the velocity of the ball, right? And we kind of get stuck there because we could divide velocity of the ball over to the other side, but it's still something that we don't need or we can't have in our equations because of what it specifies in the problem. So we need to replace this velocity of the ball. How do we do that? We use kinetic energy. So we know kinetic energy of the rod is going to equal kinetic energy of the ball. Rod has rotational kinetic energy, 1/2 I omega. Ball has linear kinetic energy, 1/2 mv squared. 1/2s cancel. I is 1/3 M1 D squared. This omega should be squared. Omega squared equals M1 VB squared. M1s will cancel with M1s, and we get 1/3 D squared omega squared is equal to VB squared. Kind of depends how we want to solve for it now. We could divide the X to the other side and then plug that in for the VB there. That might be the easier way to do it. Let's do that. Let's divide by X. So we'll get 1/3 D squared omega squared, or omega over X, is equal to VB. We'll plug that in for VB over here. So we'll get 1/3 D squared omega squared equals 1/3 D squared omega over X squared. We got to square everything out. So 1/3 D squared omega squared equals 1/9 D to the 4th omega squared over X squared. And hopefully I did all that right. Omega cancels with omega. D to the 2nd cancels with D to the 4th to make that a 2. Well, now we need to get X by itself. So X up to the other side. So X squared over 3 equals 1/9 D squared. We multiply the 3 up, X squared equals 3 over 9 is just going to be a third, d squared, and we take the square root, and x is going to be equal to d over root 3. There's our relationship there. All right. So that is the end of problem number 3. Excellent work, Mr.